example 5, a cup of coffee is heated to 160 degrees Fahrenheit, placed in a room that maintains a temperature of 70 degrees Fahrenheit. The temperature T of the coffee in degrees Fahrenheit after T minutes is given by this equation. Find the temperature of the nearest degree 20 minutes after it's placed in the room. Use a graphing utility to determine when the temperature of the coffee will reach 90 degrees Fahrenheit. And I want to say it's Newton's law of cooling, I believe, is possibly what we're using here. Somebody's law of cooling, I think it's Newton. Anyway, here's the idea. The room's going to stay 70 degrees forever, right? Yeah. Which is colder than 160, so the temperature of the room is enough to cool the drink down. But eventually the drink's going to hit a temperature of 70 degrees. And it won't get colder than that, because once it's 70 degrees, the same temperature as the room, it gets that same. So as far as the horizontal asymptote is concerned on this one, 70 degrees is the horizontal asymptote. I'd expect that to happen. Also, when you consider something cooling, it tends to cool rather quickly to begin with, because the temperature variance is so much. And then as time passes on, it's getting less and less variance, so it's cooling it slower. So anyway, that's just a couple just trivial things about that. I don't know if I can grab the right thing up here. There we go. So if I type in my equation that they give me, T represents temperature, that's my Y1 is temperature now. And then if I type in 70 plus 90, E, and anytime you need to use E, use the second button and then ln. So it gives you the exponent. There's another E over here right above the division. That's just E, not to a power, so you have to hit the caret button and all that stuff. So if you're going to have a power on, which you usually do, just second ln. And then negative 0.0485, and then x. Big T is temperature, little t is time. Y1 is temperature, x is time. Okay, so again, just interpreting it properly for your calculator. And it says to find the temperature 20 minutes after it's placed in the room. So if I go to my table and I let x equal 20 minutes, we find the temperature is 104.12 degrees, and it says to the nearest degree, so 104 degrees. So part A, all they're asking me really to do is T of 20, and 104 degrees Fahrenheit will be the approximate temperature of the coffee at that point. Really no work to be shown. If you just maybe, if you were showing work, you might say that Y1 equals 70 plus 90 E caret parentheses negative 0.0485 x. Just show me what you entered in your calculator for that, and then establish what it is you did in order to find the answer. And then it says use a graphing utility to determine when the temperature of the coffee will reach 90 degrees Fahrenheit. So here's how you do that. And I'm going to go to my window. I already know that the temperature is 104 degrees at 20 minutes later, and it's not getting hotter, right? It's not all of a sudden going to start getting hot again, right? Temperature, all of a sudden the sun comes a little closer to the room, the temperature, no, the temperature maintains 70 degrees, so it's going to be continually cooling until it gets to 70, right? So I know it happens sometime after 20 minutes, so I'm going to go window, I'm going to go from x equals 20 to x equals, let's say 50. I'm assuming by 50 minutes it's going to drop that extra 14 degrees, right? And maybe it does, maybe it doesn't, we'll find out. And then scale, make it whatever, I got 10 right now. Now as far as y min and max is concerned, I know at 20 it's 140 degrees, right? So let's go, and the minimum it can be is 70. So let's go from 70 to 104. And there's no magic numbers here, but if you just pick the lowest and pick where it's at, you know, that should be pretty good. Scale it however you want to. I'm going to go 5 on that scale. And if I hit graph right now, there's my graph, and there's the cooling of the coffee going on there. Again, the 70 was right here, right? 75, 80, 85, 90. 90 is right in here somewhere. And I can't really tell, maybe it's around 30 or so, I don't know. To get the exact number, it's not very hard to do that. Go back over here to y. What does y1 equal?
Y1 equals temperature.
Y1 is temperature, right? We want the temperature to be 90, right? So I'm going to make a second temperature equation that says y2 is equal to the temperature we want to have, 90. Hit graph again, and now not only do you have your coffee temperature, the blue line, you also have a red line which represents 90 degrees Fahrenheit. Where those two lines intersect represents the actual time and temperature, right? So if I go to my calculate, second calc, and I'm choosing intersect, number 5, all intersect wants is 3 things. It wants to know which 2 curves you're using. That'll be the blue and the red. There's only two curves on there, so enter, 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 it jumps to the other one, enter again. Then it wants a guess. There's only one point of intersection also. It doesn't even matter what you guess. It's enter a third time, and it jumps right to it. Looks like 31.011905, comma 90. That's the point of intersection of that. X being the time, 31 minutes, and Y equals 90 being the temperature. It says when the temperature of the coffee will reach 90. So it doesn't specify any number of decimal places, right? So let's go with a couple decimal places. So 31.01 minutes. The main key to the word problems in this section is going to be an understanding of the variables and knowing what the variables represent. And no that E is not a variable, it is a number. It's a very special number that's exactly 2NDLN. That's what E is. All right, it's 2.7182818286. I don't even know what comes after the 6. It's actually 4 or 5 something, but the next number is a big enough number to bump it up to 6. But just know that it's some transcendental number, just like pi 3.1415, just this number that we just accepted in 4th or 5th grade, that's just this magical number that happens. This is a magical number that happens. Know that that's what E represents anytime you see E happening in these problems. If they happen to ask you about a horizontal asymptote here, just if you look and see what happens here, I'm going to take this Y equals 90 out of here. If they want to know a horizontal asymptote, you want X to go forever. So make X go really big, it's like 1,000 would be a big number. I'm going to go by hundreds now instead of tens. And let me drop this down to 65, just so we can see the bottom. Hit graph. And notice that it just flattens out. It eventually hits a point where it's not dropping down anymore. It still is dropping down, but it's dropping down so incrementally small you can't tell it's dropping down. So it's pretty much a horizontal line there. And if you want to know what that number is, if you just come to your table and type in a big number like 1,070. It's really 69 or 70.00000. There's a bunch of zeros, 1 eventually. But just know that it's going to be close to 70, just a tad bit above 70, but it's leveling out at 70. That's the horizontal asymptote. So if you need to see a horizontal asymptote, it's very obvious. At some point the graph's going to go horizontal. That's a horizontal asymptote. If it goes down and then starts going back up, that's not an asymptote. That's just a low point. Okay? That'd be the situation where the sun actually got close to the earth, maybe go back up. You place it inside a microwave oven, maintaining temperature 7 degrees, the sun hit a start, and all of a sudden it's temperature. So anyway, so just know that horizontal asymptotes, that's how you find them with these graphs. If you just let X get really big, is it approaching is it leveling off at some horizontal number, or is it continuing to go up forever or whatever? So that's what it's looking for in that kind of question.